Hey everyone, I am really glad you are here. Today we are going to talk about what the universe is made of. A question that sounds simple, but when you start to look deeper, it stretches into something enormous, mysterious, and beautiful. Before we begin, if you enjoy exploring the mysteries of the universe with me, feel free to like and subscribe. It helps the channel. And tell me in the comments where in the world you are watching from. It is always amazing to see people from different places looking up at the same sky and wondering about the same questions. All right, now that we have that covered, let us take a deep breath, relax for a moment, and look at what everything around us is really made of. When you step outside at night and look up, it feels like you are seeing almost everything that exists. A sky full of stars stretching endlessly in every direction, each one glowing like a tiny fragment of forever. But what your eyes see is only a fraction of the truth. The universe is not just the bright dots scattered across the darkness. It is the darkness itself, the invisible fabric that holds the stars together, the space between the atoms that form every part of your body. Everything you have ever touched or known is made from the same ingredients that light up the night sky. The same cosmic dust that drifts through galaxies, the same ancient matter born when time itself began. Billions of years ago, before there were galaxies, before there was light, before even the first atom had formed, the entire universe was compressed into something impossibly small, a dense sea of energy and potential. Then, in the moment we call the beginning, space itself began to stretch, not into something, but from something. There was no outside, no before, only expansion. The early universe was pure energy, glowing, pulsing, unimaginably hot. As it cooled, the first particles began to form. Protons and neutrons and electrons, the simple seeds of everything that would follow. Hydrogen and helium appeared first, and for a long time, that was all the universe was. Vast clouds of invisible gas waiting for gravity to pull them together. When those clouds finally began to collapse, they formed the first stars, immense spheres of burning light that lit up the darkness for the first time. Inside their hearts, under unimaginable pressure, hydrogen fused into helium, and with that fusion came light. Those first stars were the universe's first alchemists, turning the simplest elements into heavier ones, like carbon and oxygen and iron, the ingredients that would later form planets, oceans, trees, and you. When those stars died, they exploded, scattering their newly forged elements across space, mixing them into the cosmic dust from which new stars and worlds would be born. So every atom in your body has been part of a star before, and one day it will return to the stars again. But even with all those stars and planets, all the glowing nebulae and swirling galaxies, that visible matter makes up only a small slice of what the universe truly contains. When astronomers measure the way galaxies spin, they find that something unseen is holding them together. There is not enough visible matter for gravity alone to explain their motion. That missing ingredient, that invisible mass, is what we call dark matter. It does not glow or reflect or absorb light, but it bends gravity's path, shaping the structure of the cosmos like an invisible skeleton. It surrounds every galaxy, cradles every cluster of stars, and yet we cannot touch it, cannot see it. We only feel its pull, gentle but constant, across billions of light years. Then there is something even stranger, something that fills all of space and pushes everything apart. Dark energy. While dark matter holds galaxies together, dark energy drives them away from each other, stretching the universe faster and faster. It is a kind of pressure built into the very fabric of existence, an unseen force that accelerates the expansion of everything. We do not know what it is. It could be a property of space itself, or a hint of deeper dimensions, or something we have not yet imagined. But it makes up almost 3/4 of all that exists. The universe, in other words, is mostly made of things we cannot see and do not yet understand. If you could take the entire universe and break it down into percentages, only about 5% would be ordinary matter, the kind that makes up planets and people and stars. About 27% would be dark matter, and roughly 68% would be dark energy. So the next time you look around you, remember that everything you can see, every tree, every grain of sand, every shining star, belongs to that tiny visible fraction. The rest is invisible, silent, and yet absolutely essential to the story of existence. Even the space between stars, the vast emptiness that seems so still, is not truly empty. Tiny particles flicker in and out of existence, appearing and vanishing in moments shorter than we can measure. Energy hums softly through the vacuum, a quiet background song that never stops. The universe is alive with this hidden activity, even in its most peaceful corners. When you breathe in, you are breathing the dust of stars. The oxygen in your lungs was born in the heart of some long-dead sun. The calcium in your bones, the iron in your blood, the carbon in your skin, all of it was once part of something that burned with the light of creation. You are not separate from the universe. You are made of it. You are the cosmos, thinking, wondering, and looking back at itself through human eyes. So what is the universe made of? It is made of matter and light, of darkness and energy, of beginnings and endings, of questions and wonder. It is made of stories written in the language of atoms and time. It is made of every heartbeat, every explosion of a dying star, every photon crossing the endless void. It is made of the same things that make you who you are, because you are part of it, inseparable, eternal, and still unfolding. When you close your eyes tonight, remember that somewhere, far away, the light of a distant galaxy is still traveling toward you, carrying the story of its birth across billions of years. And when that light finally reaches your eyes, for just a moment, you and that ancient galaxy will be connected, made of the same stuff, bound by the same universe that began in a single moment and continues to expand forever. Can the universe ever truly lose anything is a question that begins quietly, almost innocently, but it expands into one of the most profound mysteries about existence, matter, energy, and the very nature of reality itself. On the surface, we might imagine loss as a simple idea. A star dies, a planet is destroyed, light fades, or a particle drifts away into the void. Yet in the vast cosmic scale, where time stretches across billions of years and distances are measured in light years and beyond, loss is far more complicated than it seems. The universe, in its essence, is a web of conservation, transformation, and endless motion. Consider a star that dies. To the naked eye, it may seem as though it disappears, vanishing from the night sky in a burst of light or a collapse into darkness. But the matter and energy that composed it do not vanish. The star may explode as a supernova, scattering its enriched elements across interstellar space. Those atoms, forged in the heart of the star, become part of new stars, new planets, even new life. The carbon in your body, the iron in your blood, may once have been part of a star that died billions of years ago. Nothing is truly lost, it only changes form. Matter and energy are the universe's fundamental currency, conserved through every transformation, flowing endlessly from one state to another, weaving the story of existence in threads that never break. Even light, which can travel across unimaginable distances, is not truly lost. A photon emitted from a distant galaxy may journey for billions of years through the expanding cosmos, its wavelength stretched by the universe's expansion, its energy diluted across time and space. Eventually, that light may be absorbed by an atom, recorded by a telescope, or scattered into a new direction. It is never gone. It merely participates in the universe's ongoing dance, carrying its history and energy into the next interaction. In this sense, loss is only apparent, a matter of perception rather than reality. Black holes provide perhaps the most dramatic challenge to our intuition about loss. When matter falls into a black hole, it seems to vanish forever from the universe we can observe. Yet even there, the universe may not truly lose it. Stephen Hawking proposed that black holes emit radiation, now called Hawking radiation, slowly leaking energy and information back into the cosmos. Over unimaginable timescales, black holes might evaporate entirely, returning their contents to the universe in a different form. Even the most extreme apparent disappearance is not absolute. The universe has ways of reclaiming, transforming, and redistributing everything. Entropy, the measure of disorder and the arrow of time, complicates this further. In every process, from the smallest chemical reaction to the formation of galaxies, energy spreads and disperses, and things become less ordered. To human eyes, this can look like loss. A star burns out, a forest decays, a civilization fades. But entropy is not destruction, it is transformation. The energy remains, the matter remains, even as its arrangement changes. The universe is never truly empty. It only evolves, shifting forms, spreading influence, and cycling through processes that never end. Even the vacuum of space is not truly empty. Quantum physics shows us that what seems like nothing is actually a seething foam of virtual particles appearing and disappearing, energy fluctuating, and fields vibrating. The universe never has nothing. It may appear empty, but even emptiness is a kind of presence. In this way, nothing is ever truly lost, because absence itself is a kind of existence, part of the ongoing dynamic of space and energy. Time adds another layer to the question. What we consider lost in the human sense, a memory, a person, a moment, remains woven into the fabric of the universe in subtle ways. The gravitational effects of an event ripple outward. The photons emitted remain traveling through space, carrying information. The consequences of every action are encoded in matter, energy, and the curvature of space-time itself. The universe is a ledger, recording every interaction, every particle, every flicker of light. In this cosmic bookkeeping, nothing is ever truly erased. The philosophical side of this question is even more profound. When we grieve the loss of something or someone, we feel absence keenly. But in a larger sense, the universe is a vast continuity where energy, matter, and information never vanish. They merely transform. The memory of what was is encoded in countless ways, from the atoms that composed it to the light it emitted to the gravitational waves it left behind. Loss, from this cosmic perspective, is a human lens applied to a reality that does not operate by our perception. Even on a cosmic scale, as stars burn out, galaxies drift apart, and black holes dominate, nothing truly disappears. Energy may change form, matter may scatter, and light may fade beyond detection, but all of it remains part of the universal story. The universe is more like a river than a container. Water never leaves, it only flows, mixing and moving, forming whirlpools, pools, and currents, but never truly ceasing. In this metaphor, loss is only a temporary perception, never an ultimate reality. In contemplating this, we might realize that everything we see, everything we feel, and everything we measure is part of an ongoing cosmic cycle. The universe is a storyteller that never forgets, preserving its history in matter, energy, and the very geometry of space and time. From the tiniest particles to the largest galaxies, from the first photons of the Big Bang to the light being emitted now from the edges of the observable universe, everything continues to exist, continues to move, continues to transform. So, can the universe ever truly lose anything? In the deepest sense, no. What we perceive as loss is only change, transformation, dispersal, or distance. Matter becomes new matter. Energy becomes new energy. Light becomes absorbed, scattered, or stretched. Every event, every particle, every wave of energy is recorded, transformed, and preserved in some form. The universe is not a vault that loses its contents, but a symphony in which every note echoes forever, resonating through time and space in ways we may never fully grasp, but which continue endlessly without true disappearance. Loss is human, impermanent, and local. The universe is eternal, cyclical, and infinite in its transformations. Everything, from the smallest atom to the grandest galaxy, from the first photon ever emitted to the furthest reaches of dark energy, is part of a continuum that never ends, that never forgets, that never truly lets anything vanish. In this light, loss is an illusion, a momentary shadow in the endless dance of existence, a reminder that the universe preserves all, carries all, transforms all, and in doing so, never truly loses a single thing. Could there be light still traveling from the first star ever born is a question that stretches the mind across time and space in ways almost impossible to fully imagine. The first stars did not shine yesterday, or even millions of years ago. They lit up the universe in its earliest childhood, when everything we know, from galaxies to planets to humans, did not yet exist. Their light began its journey when the cosmos was a hot, dense, and expanding cloud of gas, slowly cooling and coalescing into the first structures that would form the framework of everything that came afterward. And some of that light may still be traveling through the void even now, billions of years later, as a faint whisper of the universe's first awakening. The first stars, called population 3 stars by astronomers, were unlike any stars we see in the night sky today. They were enormous, many times the mass of our sun, burning with an intensity that is almost unimaginable. Their fuel was hydrogen and helium, the simplest and most abundant elements produced in the Big Bang, and they forged the first heavier elements, like carbon, oxygen, and iron, that would one day become the building blocks of planets, life, and even you. These stars burned fiercely, living fast and dying young. Some may have exploded as supernovae, scattering those newly formed elements across the surrounding space, while others may have collapsed into the first black holes, leaving dark reminders of their presence. The light emitted by these first stars is traveling still, stretching across the vast reaches of space. Because the universe is expanding, that light is stretched as well. Its waves grow longer, shifting from the ultraviolet or visible spectrum into the infrared and beyond, moving farther away from the energies that originally left the stellar surface. This expansion means that even if the star itself no longer exists, its photons continue on their endless journey, carrying information about an epoch that is otherwise entirely inaccessible to us. They are like messengers from a time before our sun shone, before Earth formed, before the first atoms in your body existed. To put this into perspective, consider that the universe is roughly 13.8 billion years old. The first stars likely formed only a few 100 million years after the Big Bang. That means the light we might detect from them has been traveling for over 13 billion years, traversing the empty expanses of space, passing through regions that would one day become galaxies, stars, and planets. Some of it may have already reached telescopes like the James Webb Space Telescope, revealing tiny patches of early light, ancient signals from a time when the cosmos was still young, strange, and unfamiliar. But even detecting this light is not straightforward. The first stars were not isolated. They formed in dense clusters within primordial clouds of gas. Their light had to travel through fogs of hydrogen and helium, sometimes being absorbed or scattered before it could escape into the broader universe. And then, as the universe expanded, that light stretched, dimmed, and cooled, becoming fainter with every passing eon. The photons are still there, but they are traveling in a vast sea of darkness, a cosmic ocean in which distance is measured not just in kilometers or miles, but in billions of years of travel time. There is also the remarkable idea that this light is carrying with it more than just brightness. Every photon encodes the story of the star that created it. Its color, its energy, its polarization, all of these carry information about the temperature of the star, its mass, its chemical composition, and the environment around it. When that ancient light reaches us, we are effectively looking at a cosmic fingerprint, a record of conditions that existed at a time when the universe was only a fraction of its current age. We are seeing the past directly, a visual echo of the moment when the first nuclear furnaces ignited and began to transform the universe forever. Now imagine tracing that light through time. Each photon has traveled across an expanding cosmic web, through the gravitational influence of dark matter, around the warps and curves of space-time, sometimes bent by massive objects along the way. Some light may have skirted entire galaxies. Some may have passed near black holes, stretching and bending as it went, carrying subtle distortions that tell the story of the universe's structure as much as the story of the star itself. The light of the first stars is not merely a beam. It is a thread woven into the cosmic tapestry, linking the universe's earliest moments to the universe we inhabit today. Even more astonishing is the thought that the journey of this light is still ongoing. There are regions of space so far away that their light will not reach us for millions or even billions of years more. Somewhere, photons that left the first stars are still moving, traveling at nearly 300,000 kilometers per second, crossing the void in silence, oblivious to time, oblivious to galaxies, to planets, to life. They are ancient travelers, bearing witness to the birth of cosmic structures, racing through emptiness toward destinations they may never reach, because the universe itself continues to expand beneath them. And in a way, this light is infinite in its meaning. Even if we never detect every photon from the first stars, the possibility that it exists, traveling endlessly, reminds us of the continuity of the cosmos. Every photon is a survivor of unimaginable timescales, a witness to events that shape the very fabric of reality. They link us to a past so distant that it challenges the human mind, and yet, through observation, through careful measurement, through imagination, we can grasp at least a fraction of that story. The first stars and their light also teach us something profound about the nature of time. We tend to think of the past as fixed, gone, no longer present. But light shows us that the past is still moving, that it travels, that it arrives long after it was emitted. In a very real sense, the universe allows us to see history itself, to connect with moments that no longer exist except in the photons they produced. That is why the question of whether light from the first stars is still traveling is more than a physical inquiry. It is a meditation on the persistence of reality, the endurance of energy, and the continuity of the universe across unimaginable spans. Even more, the light from the first stars sets the stage for everything that follows. Without those early stars, there would be no supernovae to scatter heavier elements, no nebulae to form the next generation of stars, no planets, no life, no humans to wonder about it at all. That light, still moving across space, is a reminder of causality writ large, of beginnings that ripple across billions of years, shaping the universe in ways both subtle and profound. Every beam is a thread connecting the birth of the cosmos to the moment you read these words. So could there be light still traveling from the first star ever born? The answer is yes, in every sense that matters. It moves now, silently, across the void, stretched and faded by the expansion of space, carrying secrets of creation, holding the history of the first moments of stellar fire. Some of it has already reached us. Some is on its way, and some may never touch our eyes. Yet all of it continues to exist, part of the ongoing story of the universe, a luminous bridge connecting the dawn of time to the present moment and beyond, into the endless future where the cosmos itself keeps expanding, carrying those first photons ever onward toward eternity. Could there be other universes beside ours is one of those questions that quietly unravels everything we think we know about existence itself. It begins as a whisper in the mind, a small wondering about what might lie beyond the edge of everything. But once you start to follow it, it expands into an idea so vast that it could contain infinite realities, each with its own laws of physics, its own forms of matter, and maybe even its own versions of life. It is a question that does not just ask what is out there. It asks what it means for something to exist at all. When we speak of our universe, what we are really talking about is all of space and time as we can observe it. It includes every galaxy, every particle, every wave of light, and every moment from the Big Bang until now. But even within that description, there is an assumption, a quiet belief that this totality is the whole story. And yet physics, when pushed to its furthest boundaries, begins to whisper something different. It suggests that our universe might not be the only one. It might be part of a much larger cosmic landscape, a grand multiverse where countless universes bloom and fade like ripples on an infinite ocean. To understand this, we can start with the idea of cosmic inflation. In the earliest moments after the Big Bang, space did not expand slowly and steadily the way it does now. It expanded at a rate faster than light itself, in a kind of sudden, overwhelming burst of energy. This inflation smoothed out the universe and set the stage for galaxies and stars to form. But some theories suggest that inflation might not have ended everywhere at once. Instead, it could still be happening in distant regions of space, endlessly creating new universes in an eternal process of cosmic growth. Each bubble that forms in this inflating sea could become its own universe, separate from ours, each with different properties, different constants, and maybe even different dimensions of reality. Imagine space as a vast field of potential, an infinite frothing ocean of quantum energy. Within it, tiny fluctuations can trigger the birth of new universes, like bubbles appearing in boiling water. Each bubble expands, cools, and becomes a universe with its own space, time, and laws of nature. These universes might drift apart, forever unreachable from one another. To an observer inside any one bubble, it would seem like the only universe that exists. But from a higher, impossible perspective, there would be countless such bubbles scattered through the endless cosmic foam. If this idea is true, then our universe is not a solitary creation but one among uncountable others, perhaps each with its own unique story. Some could be like ours, with galaxies and stars and life. Others might be unimaginably different, built from forms of matter or energy that we could never recognize. Some could collapse seconds after they are born. Some might expand forever in total darkness. In some, the laws of physics could prevent atoms from forming at all. And in a few, the conditions might be perfect for life to arise again. Perhaps even intelligent beings asking the same question we are asking now. There are also quantum reasons to suspect that multiple universes might exist. In quantum mechanics, every particle exists in a superposition of possibilities until it is observed or measured. According to one interpretation, the many worlds interpretation, when a quantum event can have multiple outcomes, all of those outcomes actually occur, but in separate branches of reality. Every time a decision is made, every time a particle takes one path instead of another, the universe splits, creating new versions of itself that carry on independently. In one, you turned left. In another, you turned right. In one, the star explodes. In another, it burns quietly. All possibilities are realized, each in its own version of the universe. If that is true, then there could be infinite versions of you, infinite histories, infinite futures, each unfolding simultaneously, each unaware of the others. It would mean that reality itself is a vast branching tree, with every quantum moment splitting into new twigs and leaves that stretch endlessly in all directions. The multiverse, in this sense, would not be a distant cosmic space, but something woven into the fabric of existence itself, branching at every instant. Then there are ideas from string theory, which suggest that what we call our universe might be just one slice of a higher dimensional space. In this picture, universes could be like sheets or membranes floating in a larger dimensional realm. These sheets could occasionally collide, triggering events like our Big Bang, creating new bursts of energy and new universes in the process. Somewhere, drifting parallel to us, there could be other universes moving through this higher dimensional space, separated from ours by distances not in kilometers but in extra dimensions we cannot perceive. The most haunting part of this idea is that we might never be able to reach or observe these other universes directly. The distances between them could be infinite. The boundaries that separate them might be absolute. The laws of physics in our universe might prevent any kind of travel or communication beyond our cosmic bubble. Yet their existence could still leave traces, subtle fingerprints on the fabric of our universe. Some cosmologists have searched for these signs, tiny anomalies in the cosmic microwave background, the faint afterglow of the Big Bang, that might hint at collisions or interactions between universes in the distant past. So far, the evidence is not certain, but the possibility remains. Even philosophically, the multiverse idea challenges our sense of meaning. If there are infinite universes, each with different versions of us, then what does it mean to be this version in this particular universe? Are we unique, or are we one of endless copies, all living out slightly different possibilities? Some find this thought unsettling, but others find it deeply beautiful, because it suggests that existence is not a single fragile miracle, but an infinite tapestry of miracles, woven together by the laws of nature and the quiet unfolding of possibility. And even if we never prove the existence of other universes, the very act of asking this question reveals something profound about us. It shows that our minds are capable of stretching beyond the visible, reaching into the unknown, imagining not just new worlds, but entirely new realities. It shows that the universe has given rise to beings that can contemplate not only where they are, but where everything else might be. Perhaps the truth is that the idea of other universes is not about distance or location, but about potential. The universe we see is vast, but it is still finite in what it can contain. The human mind, however, can imagine infinity, can hold in thought an endless collection of worlds, each different and each complete. That, in itself, might be the deepest reflection of the multiverse, not outside of us, but within us, in our capacity to dream and to wonder. So, could there be other universes beside ours? The answer might be yes, or it might be something even stranger, something beyond any of our current theories. What we call the universe could be just one verse in a cosmic poem without end, a single note in an eternal symphony that never repeats, always expanding, always creating. And if that is true, then everything we know, every galaxy, every life, every thought, is just one small part of an infinite sea of creation. When you look at the night sky and see the stars scattered across the dark, try to imagine that beyond that darkness might lie other skies, other stars, other versions of existence entirely. You might never see them, but perhaps they are there, shimmering in silence, just out of reach, forever connected through the same mystery that brought this universe and us into being. How old is the universe in human years is a question that sounds so simple that we almost expect a quick number, an age we can say out loud and be done with. But when we start to think about what that number actually means, It opens into one of the deepest and most humbling realizations the human mind can ever face. Because when we try to measure the age of everything that exists, we are not just counting years. We are tracing the heartbeat of reality itself, the flow of time that began before there were clocks, before there were suns, before there was even space to measure. If we translate the age of the universe into human time, the answer most scientists give is around 13.8 billion years. But to really understand that, to feel what that means, we have to stretch our imagination far beyond anything in our daily lives. Think of the oldest trees on Earth, those ancient bristlecone pines that have stood for nearly 5,000 years. To them, a century is a heartbeat. Think of the pyramids, rising in the deserts of Egypt more than 4,000 years ago, when the stars above looked almost the same, but the people who gazed at them were just beginning to ask the same questions we ask now. From their time to ours is only a blink in cosmic history. Even if you took all of human civilization, from the first fires to the age of computers, it would barely register as the faintest spark in the timeline of the universe. Let us try to imagine it as a kind of calendar. If the entire history of the universe, from the Big Bang to now, were compressed into a single year, the Big Bang would happen at the first instant of January 1st. Galaxies would begin forming by mid-January. Our Milky Way would take shape around May. The Sun and Earth would not appear until early September. Life would start later that month, first as tiny single-celled organisms. Complex life, with bones and shells, would not arrive until mid-December. Dinosaurs would walk the earth just a few days before New Year's Eve, and all of human history would unfold in the last seconds before midnight. Everything you know, every story ever told, would flash by in that final heartbeat of the cosmic year. When we say 13.8 billion years, what we really mean is that 13.8 billion Earth orbits have passed since space and time themselves began expanding from an unimaginably hot and dense state. That event, the Big Bang, was not an explosion in space. It was the creation of space. There was no before in the way we think of it, because time itself was born in that moment. As the universe expanded and cooled, energy turned into matter, light began to travel freely, and the first atoms formed. Those atoms clumped together under gravity, forming stars that burned and died and seeded the cosmos with the heavy elements that would someday make planets and life possible. When we look into the night sky, we are actually looking back through time. The farther away we look, the older the light we see. There are galaxies whose light has been traveling for more than 13 billion years, which means we are seeing them as they were when the universe was just a baby, only a few 100 million years old. And beyond them lies a faint glow called the cosmic microwave background, the afterlight of the Big Bang itself. It is the oldest light we can see, the echo of the moment when the universe first became transparent, about 380,000 years after its birth. To put that in perspective, if the age of the universe were one human lifetime, the Earth would have formed when that cosmic person was in their late teens. Life would have appeared almost immediately, growing and changing through all the decades that followed. Dinosaurs would have ruled the middle years, and humans would have arrived only in the very last moments, perhaps just before the final breath. And yet, even that comparison fails to capture the scale of it, because the universe is not aging in a simple linear way. As it expands, time itself stretches. The ticking of a cosmic clock depends on where you stand, how fast you move, and how deep the gravity around you is. A billion years near a black hole does not pass the same way as a billion years in deep intergalactic space. So when we ask how old the universe is, we are really asking how long it has been since expansion began, measured by the flow of time in our corner of space. That is why we say 13.8 billion human years. But for other observers, in other gravitational fields or other universes, if they exist, that number might not mean the same thing at all. When you think about the early universe, it is hard not to feel awe. In its first moments, everything was so dense that matter and energy were indistinguishable. Quarks and electrons danced in a blazing plasma. There were no stars, no light as we know it, only a brilliant fog of creation. Then, slowly, as the universe cooled, patterns began to form. Gravity pulled the matter together. Tiny fluctuations grew into vast structures. The first stars ignited. They were enormous, short-lived, and bright, fusing hydrogen into helium and heavier elements before collapsing into supernovae that scattered those elements across space. Out of that dust came new stars, new planets, and eventually, us. So when you ask how old the universe is in human years, you are really asking how long it took for the atoms in your body to be forged, recycled, and assembled into living form. The iron in your blood was made inside a dying star that exploded billions of years before the sun existed. The calcium in your bones, the carbon in your cells, the oxygen in your breath, all were formed in the hearts of ancient suns that lived and died long before the Earth was born. Every human heartbeat carries the memory of cosmic time. You are made of material that is almost as old as the universe itself. Now imagine standing outside on a clear night. The stars above you are shining from different eras of the universe. Some are only a few light years away, others are thousands, a few are millions. And the faintest smudges in the darkness are galaxies whose light began its journey before Earth existed. When you see them, you are looking directly into the past. You are seeing moments frozen in time, scattered across billions of years, yet arriving together in your single present moment. That is how enormous the age of the universe truly is. 13.8 billion years is not just a number. It is a story written in starlight, in fossilized light waves still streaming through the dark. It is the time it took for hydrogen to learn how to dream, for gravity to write galaxies, for matter to think about itself. It is the age of a living cosmos that continues to evolve, one that might keep expanding and changing for trillions of years more, long after our planet, our species, and even our galaxy are gone. And yet, here we are, for a flicker of a moment, aware of it all. When you think about the age of the universe in human years, you begin to realize that time itself is not something separate from us. It flows through us, it built us, it carries us. The universe is not just old. It is timeless in the sense that its story never truly ends. Each new star that forms, each new thought that arises in a human mind, continues the same unfolding process that began when everything began. So the universe, in human years, is around 13.8 billion, but its age is not something distant and abstract. It is something you can feel every time you breathe, every time you look up, every time you wonder where it all began. You are living proof of those billions of years, a collection of ancient atoms arranged in a fleeting, conscious form, staring back at the cosmos that made them. The universe's age is written not only in the stars but also in you, because you are part of its memory, part of its unfolding, part of its 13.8 billion year story that is still being written right now. What is the universe expanding into is one of those questions that sounds so simple that a child could ask it, and yet it reaches deeper into reality than almost anything we can imagine. To even begin to picture it, we first have to step back and let go of the way our minds are used to thinking about space, as if it were a kind of stage where everything happens with edges, borders, and directions we can point to. When you look up at the night sky and imagine all those galaxies flying apart, it is easy to picture them rushing outward into some huge empty blackness waiting to be filled. But what if there is no outside at all? What if space itself is what is growing, stretching, and unfolding, and there is nothing beyond it to expand into because beyond space there is no space? Imagine a balloon. not the inside, but the surface. If you draw tiny dots on that surface and blow air into the balloon, the dots all move away from each other. None of them are traveling into some outer space around the balloon. The surface itself is stretching. The space between the dots is what grows. Now, imagine that same idea but in 3 dimensions rather than 2. Our galaxies are like those dots. The universe does not sit inside a bigger container. It is the container, and that container is changing shape. Every second, the fabric of reality itself, what we call space-time, stretches quietly, smoothly, invisibly. It is not expanding into anything. It is expanding as itself. When astronomers look at the light from faraway galaxies, they see that the light waves are stretched, their colors shifted toward the red part of the spectrum. This is called redshift, and it is how we know that the universe is expanding. The space between galaxies is literally increasing, carrying them farther apart. That discovery, made in the early part of the 20th century, changed everything. Before that, most scientists assumed the universe was static, eternal, and unchanging. Then came the realization that it had once been smaller, denser, hotter, and that it has been unfolding ever since. From that moment, the idea of an expanding universe became one of the most profound revelations in human history. But still, the question lingers in the mind. If the universe is expanding, what lies beyond its edge? The answer is that there is no edge, at least not in the way we usually imagine it. You cannot step outside the universe any more than you can walk north from the North Pole. Space curves back on itself, and everywhere within it is part of the same cosmic fabric. There may be regions so far away that their light will never reach us, no matter how long we wait, because the space between us grows faster than light can travel across it. Those unreachable zones form what we call the observable limit of the universe. Beyond that boundary lies not an outside, but more of the same infinite fabric, continuing forever, or perhaps looping in ways our current physics can only hint at. It helps to think about how strange the concept of nothing really is. We often picture nothingness as a dark void, a place where there is simply empty space. But even empty space is something. It has energy, dimensions, quantum fields, and rules. True nothingness is not a place you could ever reach, because the moment there is a place, there is something. The universe cannot expand into nothing because nothing, in the purest sense, has no location, no geometry, no outside or inside. Expansion happens within the coordinates of the universe itself, not into an external arena. Cosmologists use mathematics to describe this expansion through the metric of space-time. That metric tells us how distances between points change over time, not because galaxies are speeding through space, but because the very measurement of distance is shifting as the fabric of space stretches. It is not motion through space, but motion of space. That is why galaxies at the far edges of the observable universe can seem to move away faster than light. They are not breaking any cosmic speed limit. The light itself is carried along by the expansion of the medium it travels through. Now, if you could somehow stand outside the universe and look at it from a distance, what would you see? The truth is, you cannot stand outside because there is no outside vantage point. The universe contains everything, including the space and time that would define any possible viewpoint. To ask what it is expanding into is like asking what is north of the North Pole. The question dissolves when you realize that the coordinates themselves end at that point. The same way, the universe is expanding into itself, its own geometry evolving, its own dimensions stretching. Some physicists believe the universe may be infinite in size already. In that case, it does not expand into anything at all. Every region simply becomes more spread out relative to every other region. Infinity becomes more infinite, not by growing outward, but by thinning its density over an endless expanse. Others think the universe might be finite but unbounded, curving back on itself like the surface of a sphere. If you could travel in a straight line through space long enough, you might, in theory, return to your starting point, though it would take longer than the current age of the cosmos, which we measure as roughly 13.8 billion years. And remember, that is not the edge, only the horizon of what we can observe. You might imagine time itself behaving in a similar way. The Big Bang was not an explosion into space, but the creation of space and time together. There was no outside moment before it, no empty darkness waiting for it to burst into. It was the birth of the very stage on which all cosmic drama unfolds. As the universe expands, time flows forward and space stretches. The two are connected so deeply that neither can exist without the other. Sometimes when you look at the night sky and see those faint smudges of light, the distant galaxies that have been traveling to your eyes for billions of years, you are not just seeing what the universe looks like, you are seeing what expansion feels like. Light stretched by the growth of space itself, you are looking at history still unfolding. The photons hitting your eyes began their journey when Earth did not yet exist, when the atoms in your body were still locked inside other stars. That is what it means for the universe to expand not into something else but within its own infinite self. And maybe that is the beauty of it. The idea that everything we know, every thought, every atom, every moment of life is part of a single, continuous act of expansion. Not into some distant void, but into new forms, new possibilities, new arrangements of the same eternal fabric. The universe does not need an outside to grow. It grows from within, the way ideas grow, the way awareness unfolds, the way wonder expands in the human mind when we dare to ask these kinds of questions. So the next time you look up at the stars, remember that there is no wall, no edge, no outer space waiting beyond the universe. There is only more of this endless unfolding, more of this vast and living geometry, breathing itself wider with every heartbeat of time. The expansion is not into anything. It is everything itself stretching open, an infinite bloom that has no beginning beyond the Big Bang and no boundary beyond imagination. Can something as vast as the universe even have an edge? A place where everything stops and nothing lies beyond. A final boundary where existence itself ends and something else begins. It is a question that feels simple at first, because every experience we have as humans involves edges. A table has an edge. A planet has an edge. Even a thought feels like it begins and ends somewhere inside the mind. But the universe, the totality of everything that exists, follows rules that defy the ways we are used to thinking. When you try to imagine the edge of the universe, the moment you reach it in your mind, you cannot help but wonder what lies just past it. The thought folds in on itself, stretching into infinity, because the idea of an edge in a universe that contains all space and time does not fit easily into words or imagination. If you could somehow travel across the universe, moving faster than light, covering unimaginable distances in moments, you would see galaxies drift behind you and others appear ahead. Endless seas of stars scattered across a cosmic web. You might think that if you just kept going long enough, you would reach a wall or a border, but that is not how the universe works. Space is not like the surface of a room with walls on every side. It is more like the surface of a sphere, except in more than 2 dimensions. If you kept traveling in one direction through space, you would not hit an edge. You would eventually curve back around, not because you turned, but because space itself bends. The universe has no edge in the way a balloon's surface has no edge, even though it is finite in size. Astronomers describe this idea with the concept of curvature. The universe can be flat, open, or closed, depending on its total density of matter and energy. In a closed universe, space curves back on itself, like the surface of a ball. In an open universe, it expands forever, curving outward endlessly. And in a flat universe, space stretches in all directions without bending noticeably, continuing forever yet without boundaries. Measurements of the cosmic background radiation, the ancient light left from the first moment of creation, suggest that our universe is almost perfectly flat on large scales. That means it might be infinite, or at least so vast that its curvature is too gentle to detect. If that is true, then there is no edge to find, no border where space ends, only an endless continuation of more space beyond what we can see. The part of the universe we can observe is limited by the age of light itself. Light travels at a finite speed, and since the universe has existed for only about 13.5 billion years, we can only see as far as light has had time to travel since the beginning. Beyond that horizon, there is more universe, but its light has not reached us yet. The observable universe is like a bubble of visibility floating inside something much larger and possibly infinite. It feels like an edge, but it is not a real boundary. It is simply the limit of what light can tell us. Beyond it, space continues, filled with galaxies we will never see, each one glowing with its own stars and mysteries, forever hidden beyond our horizon. But even that bubble is not fixed. The universe is expanding, and it has been doing so since its beginning. Galaxies are moving away from one another, not because they are flying through space, but because space itself is stretching. This means that the distance between galaxies increases even without motion. There is no center of this expansion, and no edge where it stops. Every point in space sees every other point moving away, as if the entire cosmos were a rising loaf of bread, each galaxy a raisin being carried along as the dough grows. No raisin is at the center, and none are near an edge. The expansion happens everywhere, all at once. If the universe had an edge, that would imply there is something beyond it, something outside of everything. And that idea makes no sense, because the universe includes all that exists. There is no outside to everything. The edge of the universe, if it can be said to exist, would be the edge of space and time themselves, where the fabric of reality ends, and the rules we know no longer apply. But such a place may not be reachable, or even meaningful. The universe is not expanding into something. It is creating space as it expands. There is no void outside it waiting to be filled, only nothingness in a way that is not emptiness, but the absence of space altogether. The idea of an edge often feels comforting because it gives the mind a sense of completion. But the universe resists completion. It is dynamic, infinite, and constantly changing. Even if it were finite, like the surface of a sphere, it would still have no edge, only curvature that loops endlessly. If you could travel far enough, you might return to where you started, not because you turned around, but because space itself carried you in a great circle. Yet the expansion of the universe makes that journey impossible, because distant galaxies are moving away faster than light can reach them. The cosmos is too vast, too alive with motion for edges to ever matter. And then there is the question of what it means for something to have an edge in time rather than in space. The universe had a beginning, or at least a transition from an earlier state, when everything we now see was compressed into a tiny region of infinite density. That moment, which we call the beginning of time, can be thought of as one kind of edge. Not an edge in space, but in history, a point beyond which time itself cannot be extended. Yet even that may not be a true edge. Some theories suggest that the universe could have existed before that moment in another form, perhaps as a previous cycle or a quantum fluctuation from a timeless state. The edge in time, like the edge in space, dissolves the closer you look. If you could stand at what you imagine to be the edge of everything, you would not find a cliff or a wall. You would find more space stretching endlessly ahead, more galaxies drifting through the dark, more stars being born, more light traveling forever outward. The universe does not end. it only changes form. Matter becomes energy, stars become dust, and that dust becomes new stars again. Even when all the stars have burned out and only darkness remains, the expansion of space will continue, carrying the ashes of creation farther and farther apart. There will be no boundary, only an ever-deepening silence. So can something that big even have an edge? Probably not in the way we imagine. The universe is not an object floating in a larger emptiness. It is all there is, a boundless fabric of space and time stretching in every direction, without a center and without a wall. The edges we imagine are reflections of how our minds work, not how the cosmos is built. The universe is both infinite and finite, both endless and complete, depending on how you look at it. It curves, it stretches, it grows, but it never stops. And somewhere within that vastness, on a small blue planet orbiting an ordinary star, a species of curious beings looks up into the night and asks if there is an edge, never realizing that they are already within infinity, surrounded by it, made of it, and inseparable from its endless expansion. What the universe is made of is both simple and impossibly complex, a truth that stretches from the smallest particles to the largest clusters of galaxies, from the faint hum of invisible energy to the blazing fire of stars. When you look up at the night sky, you might think you are seeing everything that exists, scattered like a glittering map of reality. But what meets your eyes is only a whisper of the full story, a faint reflection of something far larger and stranger. The stars, the planets, the glowing clouds of gas that decorate the darkness, all of these together form only a tiny portion of what the universe truly contains. The rest is hidden, silent, and unseen, shaping everything while revealing almost nothing. If you could gather every star that ever existed and every planet orbiting them, if you could sweep together all the dust and gas floating between galaxies, and even the atoms that make up your own body, you would still have only a small part of what is really out there. Most of the universe is invisible, built from things that do not shine or reflect light. We call these things dark matter and dark energy, though those names are only gentle guesses at something we do not yet understand. In the earliest moments after the beginning of time, when everything was still unimaginably hot and dense, the universe was a glowing ocean of energy. Out of that sea of light, tiny ripples began to form. As the universe expanded and cooled, those ripples grew under the pull of gravity, gathering matter together into the first clumps that would one day become galaxies. The light elements, hydrogen and helium, were born during that first breath of creation, making up nearly all of the ordinary matter that exists. These simple atoms became the raw material for everything that would come after: stars, planets, oceans, and living creatures. Yet this ordinary matter, the kind that makes up you and me, accounts for only a small fraction of the total universe. The rest, the unseen majority, is made of something else entirely. Dark matter makes up about a quarter of the universe, and though we cannot see it, we can feel its presence in the way galaxies move. Stars orbit the centers of galaxies far too quickly to be held by visible matter alone, so something invisible must be there, wrapping each galaxy in a vast halo of mass that cannot be touched or seen. Without this hidden structure, galaxies would fly apart, unable to hold their shape. Dark matter acts like the invisible skeleton of the cosmos, a silent framework holding everything together, guiding the formation of stars and galaxies, shaping the very structure of space. And then there is dark energy, the most mysterious element of all. It fills all of space, not as a thing, but as a kind of pressure that stretches the fabric of the universe itself. While dark matter pulls everything together, dark energy does the opposite. It pushes everything apart, causing galaxies to drift away from each other faster and faster. The discovery of this cosmic acceleration was one of the most surprising moments in human science. It was as if gravity, which had always been known as a force that binds, was suddenly revealed to have a quiet opponent working to separate everything. Dark energy makes up nearly 3/4 of all existence, and yet we do not know what it is. It might be the energy of empty space itself, or something deeper that we have not yet imagined. It is everywhere, even in the space between the atoms of your hand, invisible but endlessly active. If we could describe the universe by its ingredients, it would look like this. About 5% is ordinary matter, the kind that builds planets, people, and stars. About 25% is dark matter, unseen but heavy with gravity's influence. And roughly 70% is dark energy, the mysterious force that drives the expansion of space. So everything we can see and touch, every glowing star and drifting cloud of gas, every mountain, tree, and ocean, belongs to that tiny sliver of visible matter. The rest is hidden, vast, and unknowable, yet it shapes everything that exists. Even what we call empty space is not truly empty. Tiny particles flicker into and out of existence for moments so brief they cannot be measured. Space hums softly with this invisible activity, a quiet energy that has been present since the beginning. The universe is alive with this background motion, subtle and eternal, even in its stillness. When you breathe in, you are breathing the dust of stars. The oxygen in your lungs was made inside ancient suns. The calcium in your bones and the iron in your blood were created when those stars exploded long ago, scattering their ashes across the cosmos. Every atom in your body has been part of a star before, and one day it will return to the stars again. You are not separate from the universe. You are a small but essential part of it, made of the same elements that light up the heavens. So what is the universe made of? It is made of light and darkness, of energy and emptiness, of questions and quiet beauty. It is made of beginnings and endings that flow into each other endlessly. It is made of the same matter that built the first galaxies and now fills your veins. When you look up at the sky, you are looking at yourself reflected back through time, built from the same atoms, held together by the same forces, and carried forward by the same mysteries. The universe is not somewhere else. It is here, within you, around you, and still unfolding in every direction, endlessly creating and recreating everything that ever was and ever will be. Is the universe flat, curved, or something else entirely is a question that stretches not only across space, but across human imagination and understanding. At first, it might seem simple. We look around us, measure angles, observe light, and might assume that space behaves in ways familiar from our daily experience. Straight lines appear straight, triangles add up to 180 degrees, and the horizon seems flat. Yet when we extend this observation beyond Earth, beyond the solar system, beyond the Milky Way, to the cosmic web spanning billions of light years, the question becomes profoundly complex, deeply fascinating, and intertwined with the very fabric of reality itself. To explore the shape of the universe, we must first understand what flat and curved mean in a cosmic context. A flat universe is one in which space follows the rules of Euclidean geometry familiar to us. Parallel lines never meet. The angles of a triangle always add up to 180 degrees, and the shortest distance between 2 points is a straight line. This might sound ordinary, mundane even, but it is extraordinary when applied to the cosmos on scales billions of times larger than anything we experience. A flat universe suggests a delicate balance between the density of matter, energy, and the expansion rate, a cosmic harmony that allows the cosmos to stretch infinitely without folding back on itself or forming a closed sphere. A curved universe, in contrast, bends the rules of geometry. In a positively curved universe, space is like the surface of a sphere. Parallel lines eventually converge. The angles of a triangle add up to more than 180 degrees, and if you traveled far enough in one direction, you might eventually return to your starting point. In a negatively curved universe, space is saddle-shaped. Lines that start parallel diverge. Triangles add up to less than 180 degrees, and the geometry feels strange, counterintuitive, almost alien. Curvature implies that the universe has a shape, a topology, a global structure that can influence the fate of galaxies, clusters, and the expansion itself. Observations suggest that the universe is astonishingly close to flat. Measurements of the cosmic microwave background, the faint afterglow of the Big Bang, reveal subtle fluctuations in temperature and density. These fluctuations encode information about the geometry of space, and when scientists analyze this cosmic relic, they find that the universe appears flat to within a fraction of 1%. Yet even this conclusion is nuanced. Flat on average does not mean perfectly uniform in every location. Local regions may curve slightly under the influence of mass, stars, galaxies, clusters, and dark matter. But on the largest scales, the overall shape appears flat, like an enormous, almost infinite cosmic sheet stretching beyond observation. But what does flat really mean for something so vast? Unlike a tabletop or a piece of paper, the universe is not a two-dimensional surface. It is a three-dimensional space, expanding over time, intertwined with the dimension of time itself. When cosmologists speak of flatness, they refer to the properties of space-time, the way light travels, the relationship between distances and angles, the influence of matter and energy on expansion. A flat universe is delicately balanced between collapse and runaway expansion, a tension encoded in the density of matter and energy relative to a critical value. It is a kind of cosmic tightrope where the universe expands forever, yet gravity and energy content conspire to maintain this balance across unimaginable scales. Curvature, however, cannot be ruled out entirely. Local distortions exist. Massive objects bend space-time, curving the paths of light and matter. Black holes warp space to extremes. Clusters of galaxies distort the paths of photons traveling billions of light years. Even if the universe is flat on average, it is a living, dynamic structure, full of ripples, waves, and distortions. Flatness at cosmic scales is a statement about the global geometry, not a claim that every inch of space is uniform or uncurved. The universe is more like a slightly stretched and rippling sheet than a perfectly smooth plane. And then there is the possibility of something even stranger. Some theories suggest that the universe could be flat, curved, or more exotic in ways that our instruments cannot yet detect. It could be finite but unbounded, like the surface of a four-dimensional balloon, where traveling far enough in one direction eventually loops you back. Or it could have multiple connected regions, a cosmic topology beyond comprehension, where the concept of inside or outside loses meaning. In this sense, the universe may be flat in its average behavior, but connected in ways that are subtle, complex, and beyond direct observation. The shape of the universe also ties into its ultimate fate. In a positively curved universe, gravity might eventually halt expansion, leading to a collapse, a cosmic contraction sometimes called the Big Crunch. In a negatively curved or flat universe, expansion continues indefinitely, carrying galaxies apart, diluting matter, and eventually leading to the cold, dark, and sparse cosmos predicted by the heat death scenario. Curvature, then, is not just a geometric curiosity. It is a clue to the destiny of everything that exists, from the smallest particle to the largest supercluster. Even on a philosophical level, pondering the shape of the universe stretches the mind. It challenges our intuition about space, about infinity, about the meaning of distance and direction. Human beings live in a three-dimensional world, constrained by walls, horizons, and landscapes. But the universe is vast, dynamic and interconnected, and its geometry defies simple visualization. To ask whether it is flat, curved, or something else is to acknowledge that our understanding is limited, that the cosmos operates on scales far beyond our everyday experience, and that even the most familiar rules of geometry can behave in unexpected ways when stretched across billions of light years. Light itself provides a window into this question. By observing distant galaxies, supernovae, and cosmic background radiation, astronomers trace the paths of photons across space. The curvature of those paths encodes information about the geometry of space-time, revealing whether the universe bends, stretches, or flows in surprising ways. The very act of observation becomes a measurement of shape, a way to perceive a structure that is otherwise invisible. And the results continually amaze. A universe that is, in its vastness, almost perfectly flat, yet alive with local curvature, subtle ripples, and dynamic motion. In the end, the question of whether the universe is flat, curved, or something else entirely is both scientific and deeply human. It invites us to imagine beyond the visible, to stretch our minds across billions of years and light years, to contemplate the architecture of existence itself. It reminds us that the cosmos is not static, not simple, and not fully knowable. Yet through observation, mathematics, and imagination, we can glimpse its form, feel its scale, and marvel at its complexity. The universe may be flat in the average, curved in the local, and strange in ways we cannot yet comprehend. A living, breathing structure that continues to expand, evolve, and challenge our understanding at every moment. So is the universe flat, curved, or something else entirely? The answer is all of the above: flat on average, subtly curved in places, and potentially more exotic in ways beyond our current understanding. It is a cosmos of incredible subtlety, where geometry and physics intertwine, where light and matter trace the hidden contours of space-time, and where every observation brings us closer to understanding the astonishing shape of everything that exists, stretches beyond sight, and continues endlessly across space and time. Can the universe ever stop expanding is a question that takes us to the very edge of human understanding. A question that stretches across billions of light years and billions of years of time, and yet it is intimately tied to the fate of everything we see, everything we know, and everything we will ever encounter. At first, it seems simple. The universe began in the Big Bang, an explosion of space, matter, and energy, and since that moment, it has been growing. Galaxies drift apart, clusters move, and the very fabric of space stretches between them. But whether that expansion could ever cease involves the delicate interplay of gravity, dark energy, matter, and the hidden rules that govern the cosmos itself. To understand the possibility of stopping, we must first consider what drives expansion. After the Big Bang, the universe was dense, hot, and energetic. Gravity worked to pull matter together, to slow the expansion, to form structures that would eventually become stars, galaxies, and clusters. Yet as the universe grew, something unexpected emerged. Observations of distant supernovae in the late 20th century revealed that expansion is not slowing, as one might intuitively expect, but accelerating. Space itself is stretching faster and faster, driven by a mysterious force called dark energy. This acceleration suggests that the universe is not simply coasting outward. It is being propelled by something intrinsic to space itself, something invisible, pervasive, and poorly understood. If dark energy remains constant, the expansion will never stop. Galaxies that are not gravitationally bound to one another will drift farther and farther apart, eventually moving beyond each other's observable horizon. Light emitted from those galaxies will never reach us, and the universe will become a cold, dark, and lonely place. a vast emptiness where each galaxy or cluster of galaxies is isolated, unable to interact with anything beyond its own gravitational domain. In this scenario, expansion is eternal, unceasing, and unstoppable. The universe does not merely expand, it expands forever, carrying everything along in an ever-stretching cosmic fabric. Yet, there are other possibilities. If dark energy is not constant, but changes over time, the dynamics could shift. A weakening of dark energy could allow gravity to regain dominance. On the largest scales, gravity could slow expansion, halt it, and even reverse it. In such a scenario, the universe might eventually collapse in a reversal of the Big Bang, sometimes called the Big Crunch. Galaxies would draw together, stars would collide, black holes would dominate, and the cosmos would shrink into an unimaginably dense state, possibly setting the stage for a new cycle of expansion. This scenario is speculative, but it demonstrates how the fate of the universe is tied to forces we are still striving to understand. The mass and density of the universe also play a critical role. In a universe with enough matter, gravity could eventually overcome expansion, halting it and perhaps reversing it. But current measurements suggest that ordinary matter and even dark matter together do not provide enough gravitational pull to stop the cosmic acceleration. Most of the universe is dark energy, which seems to push space outward relentlessly. This imbalance implies that expansion is unlikely to stop under conditions we currently observe. Yet our understanding of dark energy is incomplete. What if its properties change over cosmic timescales? Could it weaken, fluctuate, or interact with matter in ways we cannot predict? These are questions that challenge the limits of modern cosmology. Even the shape of the universe influences its expansion. A positively curved universe, like a four-dimensional sphere, might eventually stop expanding if gravity dominates. A negatively curved or flat universe, on the other hand, may expand forever. Current observations suggest the universe is nearly flat, which aligns with the notion of indefinite expansion. Yet local curvature, cosmic inhomogeneities, and the presence of unseen forces may complicate this picture. Space is not uniform. It is a living, dynamic structure, full of filaments, voids, clusters, and dark matter. These features may subtly affect the long-term behavior of expansion, though the overall trajectory appears overwhelmingly toward continuation rather than cessation. Time is another dimension to consider. Cosmic expansion unfolds over billions and trillions of years, far beyond human perception. What seems fixed in our lifetimes is part of an incomprehensibly slow and vast process. Even if expansion were to slow or halt in some distant future, it would be imperceptible to us now, unfolding over epochs that dwarf the span of stars, planets, and human civilizations. The universe's story is written on a timescale that is almost impossible to grasp, a narrative of motion and transformation stretching from the first moments after the Big Bang to the farthest reaches of future eternity. Energy plays a profound role in this story. Expansion is not merely the movement of galaxies, it is the stretching of space itself. Energy and matter respond to this stretching. Light traveling across expanding space becomes redshifted, losing energy in a way that marks the growth of the cosmos. Cosmic structures form, evolve, and sometimes dissipate under the influence of expansion. Stars burn out, black holes merge, and galaxies drift, all while the canvas of space itself stretches between them. Stopping expansion would require a fundamental shift in the balance of energy across the universe, a change in the nature of dark energy, matter, and the laws of physics themselves. Even the most subtle forces cannot be ignored. Gravity may be weak on cosmic scales, but it is persistent. Local clusters of galaxies resist expansion due to gravitational binding. Planets orbit stars orbit galactic centers, galaxies orbit clusters. These motions are small in comparison to cosmic expansion, but illustrate the delicate interplay of forces. The universe is a tapestry of motion, bound by gravity, stretched by expansion, and illuminated by light, traveling across unimaginable distances. Each force interacts, sometimes reinforcing, sometimes opposing, shaping the trajectory of the cosmos in ways both predictable and mysterious. Philosophically, the question of whether expansion could stop challenges our conception of infinity, time, and existence. If expansion halts, the universe may approach a state of balance, a pause between creation and collapse, or it may begin a reversal that reshapes reality itself. If it continues, the universe becomes ever more vast, ever more empty, and ever more isolated, a silent symphony of galaxies carried on an unceasing current of space. Either outcome stretches the imagination and confronts us with the limits of human comprehension. Ultimately, can the universe ever stop expanding is a question without a definitive answer. Yet it teaches us about the cosmic forces at play, about dark energy and gravity, about the delicate balance of matter and motion, and about the incredible scale of time and space. Current observations suggest that expansion will continue indefinitely, yet the universe is full of surprises, from unknown physics to undiscovered forms of energy. The question remains open, an invitation to wonder, to explore, and to marvel at the dynamic, expanding, and ever-changing cosmos in which we live, a universe that may drift forever or may one day pause, a universe that challenges our understanding and continues to unfold beyond imagination. Do galaxies drift like leaves on a cosmic ocean is an image that is as poetic as it is scientifically grounded. And yet even that simple metaphor only scratches the surface of the astonishing reality. Imagine the night sky not as a fixed dome, but as a vast, dynamic ocean, stretching in all directions beyond comprehension, where every galaxy is a vessel, a leaf, or a current, carried along by invisible forces that shape the fate of the cosmos itself. The universe is not static. It has never been static. From the very beginning, the Big Bang set everything in motion, hurling matter and energy outward into the darkness, setting galaxies on trajectories that continue to this very moment. Galaxies are not anchored to anything. They float in the cosmic void, sometimes solitary, sometimes in clusters, connected by filaments of dark matter that stretch across hundreds of millions of light years. Their motion is both subtle and relentless, shaped by gravity, cosmic expansion, and interactions with neighboring galaxies. Just as a leaf on a river can spin, drift, or bob depending on currents and eddies, galaxies are guided by the invisible web of the universe. They swirl in clusters, are pulled into collisions, or drift away from one another as space itself expands, carrying them farther apart with each passing eon. Consider the sheer scale of this motion. Each galaxy contains billions or even trillions of stars, with supermassive black holes at their centers, swirling gas clouds, and planets circling countless suns. Yet the galaxy itself moves, its entire mass gliding through the void over millions or billions of years. The Milky Way, our own galaxy, is traveling at hundreds of kilometers per second relative to its neighbors, slowly drifting toward the Virgo cluster in a gravitational dance that has been ongoing for billions of years. It may seem imperceptible from our perspective, but on cosmic timescales, every movement matters. Every drift is part of a story billions of years in the making. The cosmic ocean is not uniform. Space is expanding, and that expansion is accelerating due to the mysterious influence of dark energy. Galaxies that are not bound to clusters or groups are carried away from each other, the distance between them growing constantly. In some sense, they are leaves on an expanding pond, drifting apart, never to meet again. But in regions where gravity dominates, Galaxies can collide, merge, and interact in spectacular ways, forming new structures, triggering bursts of star formation, or creating colossal black holes. In these areas, the currents are turbulent, dynamic, almost stormy, and the galaxies respond like leaves caught in an eddy, swirling and spinning in complex patterns that take billions of years to unfold. Even the shape of galaxies tells a story of motion. Spirals twist gracefully, arms rotating around a central core, stars orbiting in near-perfect harmony. Yet all of this movement is nested within the galaxy's journey through space. Elliptical galaxies, often formed through collisions or mergers, drift like massive, ancient rafts, carrying billions of stars in a more amorphous structure. Irregular galaxies, shaped by tidal forces or past interactions, tumble and twist as they move, their shapes evidence of the currents and collisions they have experienced. The galaxies themselves are living records of the cosmic motion around them, but the motion of galaxies is not only governed by local interactions. The universe is threaded with dark matter, forming a vast cosmic web. Galaxies drift along these filaments, pulled toward nodes where clusters accumulate, tracing patterns that stretch across billions of light years. This web is invisible to the naked eye, but its influence is profound. Galaxies follow these hidden pathways, drifting, sometimes colliding, sometimes isolated, but always moving in response to the gravitational scaffolding of the cosmos. In this sense, the cosmic ocean is not smooth. It is structured, textured, and full of currents and whirlpools that guide the journey of every galaxy. And then there is time, which stretches all these motions beyond human comprehension. The drift of galaxies unfolds over millions and billions of years. Stars are born and die within them. Black holes grow, and entire structures evolve as the galaxies themselves move through space. A single journey might take longer than the entire span of recorded human history multiplied thousands of times. Yet despite the slow pace on human scales, on cosmic scales, this movement is inevitable, continuous, and inescapable. Galaxies do not pause, they do not rest. They drift, propelled by gravity, dark energy, and the momentum inherited from the Big Bang, traveling through a universe that itself expands and reshapes the landscape around them. Even the light from galaxies tells the story of motion. The farther away a galaxy is, the faster it appears to be moving away from us due to the expansion of space, a phenomenon known as redshift. Every photon we detect carries information about the galaxy's speed, distance, and even the rate of cosmic expansion itself. In that sense, the galaxies are drifting not only through space but also through the flow of time, and their light is a message from the past, telling us about motions that began billions of years ago and continue to this day. On the largest scales, the universe can be seen as a vast, living ocean of matter, energy, and motion. Galaxies drift like leaves, but their paths are determined by a complex interplay of forces, interactions, and history. Their journeys are shaped by the gravity of unseen matter, the expansion of space itself, and the echoes of the initial conditions of the cosmos. No leaf moves independently. Every drift is part of the cosmic choreography, a movement that connects every galaxy to every other galaxy, every star to every other star, in a pattern too vast and intricate for the human mind to fully comprehend. So yes, galaxies do drift like leaves on a cosmic ocean, but it is an ocean unlike any we know. It is a fluid of space and time, threaded with gravity and shaped by dark energy, where motion is both gentle and relentless, chaotic and ordered, immediate and slow beyond comprehension. Each galaxy carries its stars, black holes, and planets through this ever-moving sea, sometimes colliding, sometimes spinning alone, yet always drifting, always moving, always participating in the grand dance of the universe. And even as we watch from our small vantage point on Earth, the cosmic ocean continues, carrying galaxies onward through time and space, an endless, silent voyage that has been unfolding since the universe itself began, and that will continue long after we are gone. A drift without end, a movement without pause, a reminder of the vast, flowing, dynamic, and astonishing cosmos in which we live. Could the universe exist without gravity is a question that at first seems almost like a thought experiment, something to ponder in a quiet moment. But when you begin to explore it, it reveals the very foundations of reality, the architecture of matter, energy, and space itself, and the cosmic dance that has unfolded for billions of years. Gravity is not just a force that makes apples fall or keeps our feet planted on Earth. It is the invisible sculptor of the cosmos, the thread that ties everything together, the rhythm that governs the motions of planets, stars, galaxies, and even light itself. To imagine a universe without gravity is to imagine a universe without structure, without cohesion, without the very laws that allow complexity to exist. Consider the formation of stars. In every galaxy, stars are born from vast clouds of gas and dust. Without gravity, these clouds could never collapse. They would remain diffuse, scattered across space, unable to ignite the nuclear reactions that give birth to starlight. There would be no suns to shine, no warmth to reach planets, no energy to power life or chemistry. The first stars, which formed hundreds of millions of years after the Big Bang, relied on gravity to bring atoms together, to compress matter until fusion ignited at their cores. Without this invisible hand, the universe would be dark, cold, and empty, a diffuse mist of hydrogen and helium stretching endlessly, never forming the brilliant tapestries of galaxies we observe today. Galaxies themselves are gravity-bound structures. Billions of stars orbit within them, held together by the combined gravitational pull of visible and dark matter. Without gravity, galaxies could not form, could not maintain their spiral arms, their elliptical shapes, or their dense clusters of stars. They would disperse into the void, each star drifting independently, never interacting, never influencing another, leaving the universe as a sparse, structureless expanse. Gravity is the glue that binds the cosmic web together, shaping the vast filaments and voids that define the large-scale structure of everything we see. Planets and moons, the celestial bodies that give us perspective and provide the environments for life as we know it, also depend on gravity. Without it, planets could not condense from the disks of dust and gas surrounding young stars. They would not form spheres or orbits. Moons could not circle planets, and tides, which have influenced everything from the evolution of life to the stability of climates, would not exist. Life itself, if it could emerge at all, would find no stable environment, no planetary surface to settle upon. Gravity shapes not just stars and galaxies, but the very conditions necessary for complexity, chemistry, and life to unfold. Even light, which travels at incredible speed, is influenced by gravity. Massive objects bend space-time, curving the path of photons, creating phenomena like gravitational lensing. Without gravity, the universe would be radically different. The paths of light would not reveal the hidden presence of dark matter, the warping of space-time around black holes, or the bending of distant galaxies. Observations of the cosmos would be fundamentally altered, and the intimate relationship between matter, energy, and space-time would be unrecognizable. Time itself is intertwined with gravity. According to general relativity, gravity curves space-time and influences the flow of time. Clocks tick differently near massive objects compared to the emptiness of space. Without gravity, this subtle dance of time and space would vanish. The universe would lose one of its most fundamental dimensions of experience, removing the framework that gives meaning to motion, interaction, and causality on the largest scales. Even the expansion of the universe, the stretching of space itself, is understood in the context of gravity. Gravity slows the expansion in regions of mass concentration, binds clusters of galaxies, and competes with dark energy in a cosmic tug-of-war that defines the evolution of the cosmos. Without gravity, this intricate interplay would vanish. Matter would not cluster, voids would remain uniform, and the dynamic story of cosmic evolution that has unfolded over 13.8 billion years would be impossible. Imagine the universe as a symphony. Gravity is the conductor, invisible but essential, guiding the motions of each particle, each star, each galaxy into a coherent performance. Without gravity, there would be no harmony, no pattern, no dance. Everything would drift randomly, without rhythm, without cohesion, leaving only chaos in an endless void. The structures that make the cosmos beautiful and comprehensible would never emerge. There would be no order, no evolution, no complexity. Matter and energy would exist, perhaps, but only as scattered, indifferent particles in a universe too vast and empty for anything recognizable to form. Even the concepts we use to understand the universe, from orbits to black holes to planetary systems, rely on gravity. Without it, our language of physics, our measurements of mass, distance, and motion would have no meaning. Light, energy, and matter would still exist. But without the shaping influence of gravity, there would be no stars to illuminate it, no planets to witness it, no galaxies to provide context. The universe would be a formless expanse, and the story of cosmic evolution, of creation, of life, and of the interconnected web that links everything could not unfold. So, could the universe exist without gravity? The answer is that it could not exist in any form that resembles the cosmos we know. Gravity is the fundamental organizer, the invisible hand, the silent force that shapes the formation of stars, galaxies, planets, and the very fabric of space-time. Without it, there would be no light from stars, no structure in galaxies, no planets or moons, no tides, no flow of time as we understand it, and no possibility of life. The universe would still be matter and energy, perhaps, but it would be an empty, unshaped, chaotic expanse, a realm without patterns, without connections, and without the delicate balance that allows complexity to emerge. Gravity is not just a force. It is the foundation upon which the universe is built. It binds, organizes, shapes, and guides everything from the smallest atom to the largest galaxy. It orchestrates motion and evolution, dictates the flow of time and the paths of light, and provides the structure necessary for life to arise. Without gravity, the universe could not exist in the intricate, astonishing, and dynamic form that we observe. It is the silent, omnipresent sculptor of reality, the invisible thread that weaves together all matter and energy, and without it, the universe would not be a universe at all. Is there more empty space than matter in the universe is a question that seems simple at first glance, almost childlike in its curiosity, but it opens into one of the deepest and most astonishing truths about the cosmos. When you look up at the night sky, you see stars scattered across a dark canvas, glowing points of matter seemingly floating in vast nothingness. And in that darkness, it is easy to imagine that empty space is the overwhelming majority, the silent stage on which matter performs. But the reality is far more complex, far more intricate, and far more fascinating than that simple intuition can convey. To begin with, we must understand what we mean by empty space. Space itself is not truly nothing. Even in the apparent vacuum between stars and galaxies, there are traces of gas, dust, and particles so sparse that one could travel hundreds of millions of kilometers without encountering a single atom. Yet even that nearly empty expanse is not devoid of properties. Space is permeated by magnetic fields, cosmic radiation, gravitational waves, and the mysterious influences of dark matter and dark energy. It is dynamic, bending and stretching under the influence of mass, energy, and the expansion of the universe. Empty space, therefore, is not simply nothingness. It is a medium, a framework, and a participant in the cosmic story. When we measure the composition of the universe, we find that ordinary matter, the protons, neutrons, electrons, and the atoms they form, makes up only a small fraction of the total content. About 5% of the universe is ordinary matter, the stuff that forms stars, planets, gas clouds, dust, and everything that we can touch, see, and interact with directly. This is the matter that gives structure and texture to the cosmos, creating galaxies, clusters, and intricate filaments stretching across vast distances. But when you compare this to the empty regions between those structures, the sheer scale of space becomes almost incomprehensible. Vast voids, sometimes hundreds of millions of light-years across, dominate the universe, giving the cosmos a sponge-like or web-like structure, where matter is concentrated along filaments and nodes, and most of the volume is emptiness. And yet, even that empty volume is not entirely inert. It is filled with dark energy, an invisible force that appears to drive the accelerated expansion of the universe. Dark energy makes up roughly 70% of the total content of the cosmos. Its presence transforms our concept of empty space from a passive background into an active player, a substance of sorts that influences the motion of galaxies, stretches the distances between clusters, and shapes the ultimate fate of the universe. In this sense, empty space is not empty at all. It is filled with something fundamental, something that pervades every corner of the cosmos, invisible and intangible, yet utterly real in its effects. Then there is dark matter, which contributes about 25% of the universe's total energy density. Unlike ordinary matter, dark matter does not emit, absorb, or scatter light, making it invisible to telescopes. Yet it exerts gravitational influence, shaping galaxies, bending light through gravitational lensing, and helping form the cosmic web. In a way, the matter we can see the stars, planets, and gas floats within an ocean of unseen matter. Another reminder that what we perceive as empty space is filled with substance, even if that substance is inscrutable and mysterious. Consider the scale of these empty regions compared to matter. Imagine the Milky Way galaxy, a sprawling spiral with hundreds of billions of stars. Even within this dense region, the distance between stars is enormous. The nearest star to our Sun is over 4 light-years away, which is more than 37 trillion kilometers. That space is overwhelmingly empty compared to the tiny stars scattered within it. Multiply that emptiness across the billions of galaxies in the observable universe, and the volume of space that contains virtually no ordinary matter dwarfs the regions filled with stars, planets, and dust. On the largest scales, the universe is more void than substance, a cosmic lattice of matter suspended in a vast and ever-expanding emptiness. Yet even in that emptiness, light travels. Photons emitted by stars, quasars, and galaxies journey across these immense voids, sometimes for billions of years, until they reach us. Even though there may be only a few particles in a cubic meter of space, the interactions that occur across those regions, from gravitational influences to the faint hum of cosmic radiation, demonstrate that empty space is full of activity and information. Nothing is truly still or inert. Even the emptiest regions of the universe are dynamic, shaping the paths of galaxies and the fate of the cosmos itself. Quantum mechanics adds yet another layer of complexity. Even in a perfect vacuum, space is never truly empty. Virtual particles constantly flicker in and out of existence, a subtle sea of ephemeral matter and energy. Fields permeate the vacuum, and these fluctuations can have real effects, from the Casimir force between plates to the seeding of structure in the early universe. Empty space, in this quantum sense, is a teeming landscape of possibility, a canvas on which the universe paints its story, one photon, one particle, and one wave at a time. When we consider the large-scale structure of the universe, it becomes clear that empty space dominates in both volume and influence. Galaxies cluster along filaments, forming a vast cosmic web that stretches across billions of light-years, with enormous voids separating these structures. These voids are the ultimate expression of empty space, regions where matter is scarce and galaxies are few. They are enormous, quiet, and largely invisible, yet their existence shapes the flow of cosmic material, guiding the motion of galaxies along the filaments, influencing gravitational interactions, and allowing the universe to expand in the way we observe today. So yes, there is far more empty space than matter in the universe. But that emptiness is neither simple nor inert. It is a medium that stretches and curves under the influence of gravity, is infused with dark energy that drives the expansion of the cosmos, and hosts invisible dark matter that guides the formation of galaxies and clusters. Even the emptiest regions are filled with light, fields, and quantum fluctuations, making them dynamic participants in the ongoing evolution of the universe. In contemplating this, we are reminded of the scale and grandeur of the cosmos. What appears as empty to our eyes is in reality a vast, intricate, and active expanse, larger by orders of magnitude than the islands of matter we can observe. It is a profound lesson in perspective, humility, and wonder. The universe is not merely stars and galaxies. It is the enormous, silent space between them, a space that shapes the cosmos and in which every particle of matter finds its place. Is there an end to space, or does it loop forever? Is one of those questions that sounds so simple when spoken aloud. Yet once you start to think about it, it opens into a horizon that never seems to stop expanding. The moment you try to picture the end of space, the mind meets something impossible, because the very act of imagining an edge implies that there must be something beyond it, something outside, and that thought keeps stretching outward until it feels like it could go on forever. It is a question that touches both the limits of human understanding and the deepest structure of reality itself. When we talk about space, we are talking about the stage on which everything happens. Every galaxy, every planet, every atom, and every ray of light exists somewhere in this vast cosmic arena. But unlike a theater or a room, space does not have walls. It does not have corners or a ceiling that we could ever reach. The universe, as far as we can tell, has no boundary you could bump into, no invisible wall that says this is where everything stops. And yet, that does not necessarily mean it goes on infinitely either. The truth might be far more subtle, something that our everyday intuition struggles to grasp. To understand whether space ends or loops, we have to first ask what shape space itself might have. We tend to think of space as an empty nothingness, a kind of blank background. But Einstein's theory of general relativity revealed that space and time are not passive. They are flexible, dynamic, and responsive to matter and energy. Massive objects like stars and galaxies bend the space around them, curving it in ways that change how things move and how time flows. That means space has geometry, and that geometry determines how it behaves on the largest possible scale. Scientists describe three main possibilities for the overall shape of the universe. It could be open, flat, or closed. If the universe is open, then it stretches out forever, curving outward like a saddle. It has no boundary, no loop, just an endless expanse where galaxies drift farther and farther apart for all eternity. If it is flat, then space extends infinitely in every direction without curving, like an endless sheet. This is the shape that current observations most strongly support. But if the universe is closed, then it curves back on itself, like the surface of a sphere. And here is where things get strange. Because if space is curved in this way, then you could, in theory, travel in a straight line through space, never turning, never stopping, and eventually end up right back where you started. This idea is difficult to visualize because we live in 3 dimensions. But think of the surface of the Earth. It seems flat when you walk on it, yet it curves gently in all directions. You can keep walking in a straight line, and eventually, after circling the globe, you arrive at the same point. The surface has no edge, no end, and yet it is finite. A closed universe would be similar, except instead of curving in 2 dimensions like the Earth's surface, it would curve through higher dimensions that our senses cannot directly perceive. In such a universe, space would loop back on itself, forming a cosmic circuit where there is no center and no boundary. But even if the universe does loop, that does not mean it is small or simple. The scale is almost beyond comprehension. Light, traveling at nearly 300,000 kilometers every second, might need billions or even trillions of years to make a complete circuit, if such a loop exists at all. And because the universe is expanding, that path might never close. The space between galaxies is stretching faster than the light could return, which means that even if space curves back, we might never see that curvature. To us, it would appear endless, even if it is technically finite. Another way to think of it is to imagine space not as a place but as a relationship between things. Without galaxies, stars, and matter, there would be no space as we know it, because space is defined by distance and direction, by how one thing exists relative to another. In that sense, asking whether space ends might be like asking where the surface of a wave stops when the ocean is calm. Space is not an object that sits somewhere. It is the structure that emerges from the presence of everything else. When you reach for an edge, you are reaching for something that does not have a separate existence apart from what fills it. Cosmologists have tried to test these ideas by observing the oldest light in the universe, the cosmic microwave background, which is the faint afterglow of the Big Bang. If space loops, that light might wrap around and show us repeating patterns, echoes of the same regions seen from different directions. So far, the data suggests that if the universe does loop, it does so on scales so vast that we may never detect it. To our instruments, it looks remarkably flat, stretching out without limit. But flat, in cosmic terms, does not mean simple or empty. It means that the geometry of space balances almost perfectly between infinite openness and finite closure. And even if the universe truly is infinite, that idea carries its own paradoxes. In an infinite universe, there would be infinite space for matter, energy, and even possibilities. Somewhere, far beyond the distance any light could ever reach, there might be another region almost identical to ours, with galaxies and stars arranged in familiar patterns, even with someone exactly like you, living the same moment, thinking the same thought. Infinity forces us to accept that every possible configuration of matter could exist somewhere, repeated endlessly across the endless expanse. But there is another kind of looping that may not be spatial at all. Some physicists have proposed that the universe could loop in time. According to certain solutions in general relativity, space-time can curve so extremely that time itself might form closed loops, paths where an event could eventually lead back to itself. These are called closed time-like curves, and while they remain theoretical, they show how deeply connected space and time truly are. To ask if space loops is also to ask if time could loop, if the universe could eventually return to the beginning in a cosmic cycle of birth and rebirth. Ancient cultures imagined this long before modern science did. Many traditions describe the cosmos as a great circle, eternally expanding and contracting, dying and being reborn. In modern cosmology, there are even models that echo that idea. Some theories suggest that our Big Bang might not have been the first, but just one of many cycles in an infinite sequence of expansions and contractions, each giving rise to a new universe with new conditions. In that case, the universe does not have a linear beginning or end. It pulses forever, breathing in and out through the fabric of space-time itself. And yet, perhaps the most beautiful part of this question is that we can never truly step outside the universe to see its full shape. We are inside the painting, trying to describe the edges of the canvas. Every observation we make is limited by the horizon of what light has had time to reach us since the Big Bang. That horizon, the edge of the observable universe, is about 46 billion light-years in every direction. Beyond that, the universe continues, but we cannot see it because its light has not yet arrived. We are surrounded by a cosmic horizon, like standing in a vast fog. We can see only a certain distance, and beyond that, mystery. So, does space end, or does it loop forever? The most honest answer we can give is that it might be both. It could be finite but unbounded, like a sphere without an edge, looping back on itself in ways too immense for us to perceive. Or it could be truly infinite, extending forever into regions we will never know. Either way, there is no edge you could travel to, no wall where everything stops. The universe is a continuum, an ocean without shores. And that realization is strangely comforting. It means that no matter where you stand, you are always at the center of your observable universe, surrounded by light that has traveled across billions of years to reach you. It means that when you look up at the stars, you are seeing not the edge of reality, but a small portion of an endless or self-looping whole, a cosmos that may curve quietly back on itself or stretch forever outward, carrying all of time and space with it. In the end, the question of whether space ends or loops forever may not have a simple answer, because space itself may not be something that can end or repeat in the way we imagine. It may be something deeper, a structure of relationships and possibilities that always continues, changing form but never truly stopping. So when you look into the night sky and feel the immensity of it pressing quietly against your thoughts, remember that you are not standing at the edge of anything. You are already inside the infinite, part of a universe that may have no outside, no border, and no end, looping or stretching through eternity, carrying you and everything that ever was within its boundless embrace.